Hi, we are going to continue with our back converter design, and in this case we are going to see the simulation results that we obtained under ideal conditions. So we are going to work with the file that we designed in our previous video, and let's see the results that we obtained. First of all, we are going to evaluate the output voltage. So here we can see the output voltage waveform. Note that we are evaluating the output voltage up to 2 milliseconds. And as we can see here, we have the startup of the converter. Okay, initially the output voltage is 0 volts because the output capacitor is discharged, the inductor is also discharged. So we need some time. We need some switching periods in order to reach steady state conditions. Okay, here we have steady state conditions. So, well, what we are going to do is to consider an initial state, T1, that is 1 millisecond, and T2 is 1 millisecond, plus 2 times the switching period. We want to evaluate the waveforms during 2 switching periods and in steady state conditions. That's why we consider this instance. Remember, the switching period is 1 over the switching frequency. So our switching frequency is 100 kilohertz. The switching period is 10 microseconds. So basically, we are going to analyze the waveforms in a very small time interval. Well, here we have the output waveform in steady state conditions and during 2 switching periods. This is switching period 1 and this is switching period 2. Our target was an output voltage of 3.3 volts. Okay, it seems that the output voltage waveform is the correct one because it's between 3 and 4. But we need to see the waveform in detail to check the specific value we have. So what I'm going to do now is to work with a smaller voltage range. I want to focus on this range to see what is the specific value we have. Okay, here we have the result. This is the same waveform, but I am focusing on a very small voltage range. Note that here we work between 3.295 volts and 3.27 volts. So, well, apparently the output voltage is changing a lot, but it's not true. Okay, it's because we are working in that narrow voltage range. Okay, the output voltage is very constant as we saw in the previous slide. Well, here we can see the average value is more or less 3.285 volts, and if you evaluate the peak-to-peak output voltage, you will see that it's close to 16 millivolts. Well, let's see other important waveforms. Here I am representing the inductor current and the output current. So we have in our back converter we have the inductor, the output capacitor, and the load, which is a resistor in our case. So I am representing this one and this one. One of the things that we saw in the theoretical analysis of the back converter is that the average value of the inductor current is equal to the output current, and this is something that we see in this simulation result. Okay. Another thing that we studied is that during the state number 1, when we turn on the MOSFET, the current through the inductor rises. So this is something that we see here. And when we turn off the MOSFET or the switch and we turn and the diode is on in state number 2, the current through the inductor falls. So this is the thing that we see here. Okay. Moreover, you can evaluate the inductor current ripple, and you will see that is 3.03 amps, which is the specification that we must satisfy. Well, so this simulation result is similar to the analysis that we perform. Let's see another couple of waveforms. In this case, I am representing the control of the switch and the voltage across the switch. So the second waveform, the red waveform, is this one. So remember, the switch model that we are using in LTspice has a threshold voltage of 2.5 volts. It means that if the control signal is higher than 2.5, the switch is on. If the control signal is lower than 2.5, is off. So here we turn on the switch with 5 volts. Here we turn off the switch with 0 volts. We configure in the previous video this time interval to be equal to d times t switch, and this one is equal to 1 minus d times t switch, the switching period. Okay, state 1 and state 2. In state number 1, what we see is that we have a short circuit, okay, because the voltage across that switch is 0. In state number 2, the switch is off. We have an open circuit, and we see that the voltage is 12 volts, the input voltage. Well, more things. Now here we have the same waveform of the previous slide. So it's the voltage across the switch, and this one is the current through the switch that we evaluate in this way. So remember, here the switch is on, here the switch is off, on and off. When the switch is on, the current through the switch is the inductor current. When the switch is off, the current through the switch is 0. So this is something that is similar to the analysis that we perform in the theoretical videos about the buck converter. Let's do the same with the diode of the buck converter. We know that we have a diode like this one, and we are going to evaluate the voltage in this way and the current in this way. When the switch is on, state number 1, the diode is off. And when the diode is off, the voltage across the diode is 12 volts, is the input voltage. When the switch is off, the diode is on. It's a short circuit. So here is on, and the voltage across the switch, across the diode, is 0. If we check the current through the inductor, what we see is when the diode is off, current is 0. When the diode is on, the current is equal to the inductor current. So this is another result that makes sense because it's the same conclusion that we obtain with the theoretical analysis. Well, finally, I want to show you the output power and the input power. This is the instantaneous output power, okay? Is output voltage times output current, is flat, okay? The output power, the instantaneous output power, is constant because we have a constant voltage and constant current. And here we have the instantaneous input power, is input voltage times this current, okay? Input voltage times input current, or the current through the switch. As you can see, it's not constant because in the second state of the buck converter, the current is 0 through the switch. So we have this waveform. We have power and then 0. Power, some power and then 0. Okay, it's not constant. So this is instantaneous power. Why we analyze that? Because we need that those results in order to evaluate, for instance, the efficiency. The efficiency is average output power divided by average input power. So average output power is the average value of the instantaneous power, and average input power is the average value of the instantaneous input power. The good point is that we can evaluate the average values of those instantaneous powers in LTspice. If we draw the waveforms and we consider one switching period or two switching periods or three switching periods, we take the average value from LTspice and we determine the average input and output power in this way. So as you can see here, the average output power is 49.5 watts, and here we have 49.7 watts. So the efficiency is 99.5%. So it's close to the ideal analysis where we consider that the efficiency is 100%. Why we don't have 100%? Well, one reason is because the switch and the diode are not ideal, and another reason is that the measurements that we are doing when we evaluate average values and so on are not perfect. Okay, perhaps we are doing some mistakes when we perform the measurement, so that's why we don't get 100%. But it's close to the theoretical analysis. So the conclusion is that the analysis that we perform for the buck converter under ideal condition leads to the same results we obtain from this ideal simulation in LTspice. So in future videos we are going to check other scenarios for our buck converter. See you.